hello. This is the lecture number 7 in functional analysis 1, and today's topic is the uniformly convex Banach spaces. Let's start with the definition. Let me point out that the concept of uniformly convex Banach spaces, basically it is a geometric concept. So it is involving a kind of the geometric property which is intuitively clear. Let me explain it, starting with definition. And suppose let E be a Banach space then E is called a uniformly convex space only if the following conditions is satisfied. If and only if. Let's write it down. For every epsilon larger than 0, there exists a delta larger than 0, such that for every x and every y belonging to E, and now we have two conditions. If you have here x must be in the unit ball, y must be also in the unit ball, and we also assume that their distance is larger than, let's say, epsilon. Then the statement says that the x plus y over 2 must be smaller than 1 minus delta. Smaller than 1 minus delta. The picture is in order to illustrate this situation. So let me make a little ball. This is our ball. And yeah, good enough. Can we take 2 points? Let's take in the extremal cases, of course, when these points are these points are on the sphere. So that means here this is denoting the sphere. So this is our S. So this is S. So that means the S is exactly so this is the center. And here we have here the radius. The radius is equal to 1. Maybe let's put the radius in the other location here. This will be the 1. So now we connect these 2 points, and what do I have? I have here that these points are in distance not so larger than epsilon. So that distance is larger than epsilon. So they are quite far away. So now we do the following. We find the middle point, which is here, and we want this middle point to be away from the sphere. So then distance here, the distance, so this is the middle point, and distance must be here larger than delta. So this must be larger than delta. So let me come back. So here we have the middle point. This is x plus y divided by 2, and we know that in this case that point from the sphere, so that means exactly so let's write it down. That means this is exactly the point here, so will be smaller than delta. So indeed, let's check it if this is the case. If this is the case, so that means what do I claim? I'm claiming simply that x plus y over 2, so this particular and norm does it mean it is larger? That means this must be smaller than 1 minus delta. That's exactly what it says. That's exactly the condition here. Let's denote the condition of the uniform uniform convexity by star, and basically we will see the more examples later when we start talking about the LP spaces. So let me make an remark. We will prove in the coming lectures, that the spaces, that LP, all the spaces, any measure space LP, and P must be between 1 and infinity, are uniformly convex. Uniformly convex. In particular, that will mean that in particular we have that not only this spaces, since Rn as a space, let's say as an LP space on the finite set of n elements, so let's say like this, in particular that Rn equipped with such a P norm is uniformly convex, and then of course small LP as well are uniformly convex. And why do we need this uniform convexity? Because our goal is just to prove this following statement. This is the way to show that this geometric property implies reflexivity of such a space. Theorem. Theorem has the name, this is Millman-Pettis. Pettis theorem. And so like this, every uniformly convex Banach space E is reflexive. So let's start the proof. Just remember we are using this notation, so we'll denote by B the closed ball, which is smaller equal than 1 in E, and maybe make it clear that we do not mix up this notation. So this is in E, and this will be X smaller than 1. And then we also use this notation, B double star. It will be unit ball, so put it like this, psi belonging to double star. And here we have the norm of psi smaller than 1. So what does it mean that we have a reflexive space? That means we have here the duality maps. So E is reflexive. If only, let's say, by the definition, if the duality map, which we defined like J, this was from E to E star. And how it was defined? It was defined like that you take the J on X and it will be acting on F just by the formula F on X. So F here belongs to the E star. So we have it. So in order to show it that this duality map, if the duality map is surjective, and remember this duality map is an isometry, so that means in such a case we here, so since J is isometry, we have that E can be considered as a subspace, so put it clearly, E, which I can identify with J of E, is a closed subspace of E double star. Therefore, in order to show that this subspace is equal to the double conjugate, it is sufficient to show that, let's write it clearly, that JB is equal to B double star. However, we also know that JB is closed because that's an isometry. So since JB is closed, it is enough to show that, let's say, that any element from B double star is in the closure. So put it like that the B double star is equal to the closure of JB. They're closed, that means it must be. So, and that means we can rewrite the form, let's say, using the formula. So that means for every epsilon larger than 0, there exists, so maybe like this, like this, for every psi belonging to B double star, so that means this psi belongs to the closure of JB, there exists, so no, maybe like this, we have here that the psi belongs to the JB closure. This is equivalent to say that for every epsilon larger than 0, there exists an X belonging to B such that, and we have it, psi minus J of X must be smaller equal than epsilon, must be smaller equal than epsilon. So that's what we need to prove. So let us fix an epsilon larger than 0 and consider an element F. Remember, epsilon is, so let's say like this, epsilon is of norm, okay, epsilon is of norm smaller than 1. So let's say like this, and take F belonging to E star and consider so that's a functional, and maybe assume simply, maybe fix an epsilon larger than 0. 1 second. Start like this. Fix an element, that will be better, element psi belonging to B double star. But since, look, if you take psi, you can always assume that psi has the norm equal 1. If it's not, you just simply normalize it, and that will be sufficient to prove that for such a psi, the disk size. So we want to show that disk size belongs to the closure of this JB. So this will be sufficient. So that means this is an element of the norm 1. 10. Take F belonging to E star such that, let me write it down, this will be F applied, psi applied on F is actually larger than 1 minus delta over 2, where delta larger than 0 is given by the condition star of uniform convexity. But notice here, this actually is nothing, there is no mystery here, because we have here that the norm of psi is equals supreme, and you can write it down, F is equal to 1 psi of F. So by the definition of supremum, you can always find such an element F in the dual space. Such an element F in the dual space. So now I have the F, functional F, so I will be using this another type, another condition. Recall that we proved in our previous lectures that the set B, JB, which is equal, identified with the J of B, is dense in B double star with respect to the weak star topology. So this topology. This topology. So it is dense in this space. And in particular, that also means that every neighborhood of Xi, means weak star neighborhood of Xi, contains an element of B. So let's use it, and let's say like this. So defined such a weak neighborhood of, define the following weak star neighborhood of Xi, and namely we take this V, and then we need to have an element. So we have already F, so I put it like this. This is the set of all eta belonging to E double star, such that there is just only one function, this F, and this is eta minus Xi is smaller, and I can take as like that number here, delta divided by 2, which is again given by the uniform, that's the same uniform convexity condition. So that's the weak neighborhood, and consequently, since again JB is dense, repeated in sigma, so with respect to sigma E double star E star, maybe no space, sigma E double star in B double star, there exists an element X belonging to B, satisfying the property that Jx belongs exactly to V to V. So that means that's the element. Okay, call it like this, B, which must be non-empty. So there exists. So that means such an element exists. Such an element exists. Very good. So what do I want to show? I want to show, we claim that actually we have this condition satisfied. So we have here that condition. We claim that psi minus j of x is smaller equal than epsilon. Assume for contradiction. So we claim it. Put it like this. Indeed, assume for contradiction that actually we have opposites. So this element is a bad one. That means it satisfies this particular inequality. Which means in particular, look, that means this equality can be basically translated very easily. So that means simply that j of x, so the j of x is belonging, and I put here psi, and I put here epsilon times the ball, that ball, and take the complement. So that means you have here, this is the ball, make it like this is the ball B double star. Then you have here epsilon neighborhood of this one, of this ball, maybe make it red. So this is the epsilon neighborhood. So the epsilon neighborhood, so this is epsilon, so you can write it down. This is B, sorry. Complement. One second. Sorry. Something is working correct. Select, and then we have here C, and then what does it mean? This means simply that you have here, this is your element psi, and then you have a small neighborhood. So what is add the ball? So you take the ball of radius epsilon. Actually, this is a closed ball, so this is the epsilon ball. So that means this is psi plus, and this will be epsilon, and this is closed ball like that. And we claim that so we say that this inequality means that one is in the complement of that set. So that's what is written here. This is in the complement. But notice that the ball, the closed ball, B double star, is also closed with respect to the weak star topology. So this is closed. Remember that B is actually by Allogo theorem, it's compact. So this is closed with respect to the sigma E double star topology. But if you remember the weak star topology is a topology of topological vector space, so you can shift the sets and you can scale the sets and they preserve their closedness and their openness. So in this case, that means simply that set here, standing here, call it W. So this set Okay, let me make nice. Call this set W is open neighborhoods of psi in sigma E star star E star, means weak star topology. And that implies basically, again, by the same property that ball B, again, put it like this, again, since JB is dense in B double star with respect to sigma E star, like this, E star topology, we again get that we have here that the JB intersection, and now I take V and take W, so which is another, this is also neighborhood, psi belongs here, must be non-empty. And therefore, we can say it, there exists an Y belonging to B such that Y belongs here, that the Y belongs here. And that of course gives us the following things. So first of all, notice that both X and Y belong to V. So let me rewrite it. So what do I have here? I have here basically that we have here like this psi, we have here and then let's say like this. What does it mean? That means V is equal to the set of all eta such that I have here F is fixed, and then you have psi minus eta smaller than delta over 2. So let's rewrite it. So I'm getting here that F, now this is again psi, and this one is minus, and this will become J of X. Absolute value is smaller than delta over 2. Similarly, I have here psi minus J of Y, close it, smaller than delta of 2. Rewrite it, and how I can rewrite it? I can rewrite it, these things, using the property that this will be like simply, let's write it down. So this will be, did I do it? Yeah, I did it incorrectly. I did it incorrectly. You have to be careful. So that's the element of E double star, and element of star is here. So this should be like this: psi minus eta on F smaller than delta over 2. Yes, so we should be careful. So let me check if I started writing down it, if I made the same bad error before. Because we have the tendency to, you see, again, so this should be also changed. So you should change it like this. This is eta minus psi F. That's the proper way to write it. That's the proper. So this is actually incorrect order. So okay, so you see, we detected something wrong, and then, of course, they rewrite it. Since then, we can rewrite these things. So let me rewrite it. So I have here like that. First of all, this will be absolute value, and you take psi, and now J of X. So put it like this: J of X. Those are J of X. So this is J of X and J of Y. So this is J of X, and then F smaller than again smaller than eta over 2. Similarly, this is psi minus J of Y, F, and that one is smaller than delta delta over 2. I'm sorry. I'm just a little kind of upset because of this little error we did it. So that one is actually equivalent to say, so let's write it down. This is psi f minus, and here will be f x smaller than delta over 2, and that one is again similarly psi f minus, and this will be f y smaller than delta over 2. So now let's look down and let's rewrite these two inequalities again. So let's rewrite them differently. So namely, we have here the left-hand side of this inequality is still smaller than that one, so put it like that, minus f, and this is x smaller than delta over 2, and that one is psi f minus f on y smaller than delta over 2. Add them up, and then this will imply that we are getting here that 2 times psi on f is smaller, and then we have here f, and this will be x, not nice, x plus y, and this will be plus delta, which consequently can be written here. We are getting here that f, sorry, again you see this tendency, psi f is strictly smaller than f, and I put here x plus y, and then that one is over 2 plus delta over 2, plus delta over 2. But on the other hand, we still have this condition on f that we didn't use, and let me go back and recall to you, where is this condition? Where is it? Yes, it is here. So this is the condition here, this condition. So it's time to apply it now. So let's apply it now. So I will put it like this. So this condition here is larger, 1 minus delta over 2. 1 minus delta over 2. And next, I go further and I say, okay, that one is smaller equal. So put it like this. This is f, norm of x plus y divided by 2 plus delta over 2. And then since remember, we chose f to be of norm 1. So this is actually equal. And that is equal x plus y divided by 2 plus delta over 2. We look at these two inequalities, this inequality and that. So we obtain in particular that implies that x plus y 2, okay, is larger than 1 minus delta. It's larger than 1 minus delta. And now we remember we chose, since so epsilon and delta to satisfy, we chose maybe like this, 4 arbitrary epsilon like this, delta to such that it satisfies the uniform convexity condition star. So what does it mean? Let's write it down here. So this means simply the following. So if you have here x smaller equal than 1, y smaller equal than 1, yes, both of them belong to B. And then we also have here that x minus y, and we assume here, yes, look what happens here. We have here the assumptions that y belongs to this set, that means y belongs to W. So that means here y belongs to w, and that implies that this one is larger than epsilon. Then this implies that there exists, so so for every epsilon larger than 0, there exists a delta larger than 0, down, and then we have here the condition which says that x, and this one is plus y divided by 2, is smaller than 1 minus delta. Let me check it. Yeah, that's this one. So let's look again. That's exactly the condition. And we have that all the assumptions satisfied except something is wrong with the statement because we just got the exactly opposite inequality. This is not what we are supposed to get. So, in other words, let me continue. Therefore, thus, we have a contradiction. And the theorem is proved. And the theorem is proved. The theorem is proved. And there's one more proposition that follows this theorem. It is kind of useful. Therefore, maybe let's start it here. I will write this proposition. Before writing this proposition, let me recall couple of properties. Recall some properties. Of weakly convergent sequences in E. So that remember this means we are using the topology, weak topology. So this is a weak topology for this convergence. So notice that we have here, first of all, we have here that sequence is convergent weakly. So this is the notion xn converges weakly if and only if for every f belonging to E star we have here f on xn converges to f of x. Then we also have here if xn converges to strongly, this also implies that xn converges weakly. And the third property, we also have that if xn, this is, I think I wrote the wrong numbers, 2, and the third property, that if you have here xn converges to x, then this implies that x is smaller equal than limit infimum, and n goes to infinity of the norms of xn. So that means xn is also bounded, that xn is also a bounded set. So that means the set is also bounded. And the fourth property was if fn converges to f, and here we have here that xn converges weakly to x, so this would imply that fn xn converges to f of x. And now let us formulate this proposition. So the proposition is the following. Assume that that E is a uniformly convex Banach space and let xn belonging to E be a sequence such that, so here we put here two conditions. First one, xn is weakly convergent to x. So that means weakly converges to x. And the second condition, B, is that limit supremum, and then this will be n goes to infinity, of the norm of xn actually is a smaller equal than x. Then the statement is, then we have the statement, then we have here that xn converges strongly to x. And the proof, let's start it immediately. Notice that the condition B mainly means nothing else, means that the limit of xn is equal just to x. So we have here that the sequence is convergent to x, and the limit of the xn is equal to the limit of the limit. Sorry, the norm of the limit. To the norm of the limit. So this statement simply will be telling you that if you have a weakly convergent sequence such that the norms of the sequence converge to the norms of the limit, come on, they in the uniform Banach space, it will mean that the sequence itself is strongly convergent. So what is here? How to prove it? Okay, that's clearly satisfied. Look, what do we have? Here we have here a couple of properties. So first of all, remember this one. This one is always satisfied. This inequality is always satisfied. And we also have another inequality, limit supremum. So what do I have here? Write it down. So let's write it down. So we have actually this one indeed. We have here x. This is what limit infimum xn, n to infinity. And limit infimum is always smaller than limit supremum, n goes to infinity. And that one is equal xn. And that one, by the condition B, is smaller than x. So you are getting here that the limit infimum is equal to the limit supremum. So yeah, the sequence converges. So now, once we have it, we do the following. We define a couple of numbers. Now, first of all, I define the number lambda, which will be maximal value, and I take here, this is xn, or x. The x is the limit, xn. So it can be large, And the one thing I can say, we can assume that this one is larger than 0. Otherwise, there is nothing to prove. If this is not large, if it's not larger than 0, then maybe let's say like this: assume that x is not equal to 0. Otherwise, the statement follows immediately, because actually this condition, called not maybe star, I call this condition here, call it like this, cross, it follows from the cross, so it follows from cross for x equals 0. So it will be from this formula. So assume that x is not equal to 0, so clearly lambda n is positive, and then we can define the sequence yn. I put here yn, and yn by the definition will be xn divided by lambda n. So yn is the definition. So maybe it's not really nice. I will write it again. Yn, 2 dots, equals, and this is xn divided by lambda n. And we also put here y will be equal, this is x divided by the norm of x. Then clearly, since you can see immediately that yn, if I take the, that the xn is clearly smaller than lambda n by the definition. Yeah, look, this is the definition. That's here. That one is definitely definitely larger equal than xn. So we are getting here that this implies that yn has the norm smaller than 1, and we also have here that the y is having the norm 1. So one thing is clear. So now the next remark, notice that if I take this yn, I'm getting here that yn converges weakly to y. So put it like this. Indeed, we have, let's write it down, we have, so I have here the following thing. So for every f not belonging to E star, we have like this, write it down, f, and this will be equal to yn. What is this? So let me write it down. This one is equal to, and I can write it down, f, and I have here xn divided by lambda n. But that one is equal, I can write it down, f divided by lambda n on xn. So notice that lambda n, what is this? That we know that xn is convergent to x. So we are getting here that lambda n also converges to lambda. So not to lambda, to x. This is the same, by the convergence of that set. So if I denote this fn, the f divided by this particular lambda, we will be getting here that this guy converges to the limit, which is equal f divided by the norm of x. So now I have it that this convergence is strong. Strong convergence because it comes from the convergence of lambda. So now we also know that xn converges weakly to x. So you go here and you see I have the property number 4. So we have here fn, call this f0. So this will be f0 like in our formulation. And we have two things. This is strong. This one is weak. Then I have here this particular convergence. So what do I get here? I'm getting here that these two conditions implies that, let's go here, that this one, so I'm getting here that maybe do it like this, continue. So this one is, and put it like that, as n goes to infinity, converges to f divided by the norm of x, and this one is xn, which can be written as f, and this will be xn divided by norm of x, and that one is nothing else than f on y. And we just showed that this is true for every f, so we just showed that indeed indeed yn is convergent weakly to y. So yn is convergent weakly to y, and we are almost done. So now, since yn is convergent, so let me see like this. Therefore, we also have, and let me write it down, that yn plus y divided by 2 converges weakly to y. Is it clear? Yeah, let's go to y over y by 2. So this one will be equal just y. And And therefore, we have the following. So since this is convergent, so again, I go back to my properties. I go to look at my third properties. I look, oh, we have here this property. So let me write it down. So what do I have here? I have here that in such a case, the limit. So what is the limit? The limit of, maybe I'm too far, so put it here like this. Y must be smaller or equal to limit infimum as n goes to infinity. And here I have here yn plus y over 2, yn plus y over 2, and that one, oh, what is this? I can write it down simply, yn so is smaller than 1, so by triangle inequality, this one, yn smaller than 1, also y is actually equal to 1. But both smaller than 1, then I can write it down, 1 divided by 2, which is equal to 1. And we already know that that one is equal to 1 by the definition. So what do I get here? We obtain that this limit exists. Oh, maybe I should do it more correctly. Write it down correctly. Yeah. Suppose, okay, write it down everything correctly. Lim supremum n goes to infinity. Yeah, we cannot miss this step. Over 2, and now smaller than 1 plus 1 over 2, which is 1. And then 1 is equal to 1. So we have that the values yn plus y over 2 is convergent to 1. So this is convergent to 1. That one is convergent to 1. Yeah, that's here. Limit exists. This is the same. This is the same. So this limit must exist and is equal to 1. That's very good. On the other hand, we claim that this would imply that yn plus, minus y must be convergent to 0. Must be convergent to 0. Suppose it is not convergent to 0, indeed. Suppose it is not convergent to 0. So what would I get here? So that means there exists a subsequence nk such that nk minus y would be larger or equal to a certain epsilon, larger than 0. So suppose it is not. For contradiction, very good, but again, then by the uniform convexity condition, star, what would I get? I would say we have this, there exists a delta larger than 0 such that yn k minus y becomes plus, I should like plus y divided by 2 is smaller, 1 minus delta. But look, that's not possible. This means it would be true for every nk, so for every k equals 1, 2, so the whole sequence. But that's not true because here, in this condition, we have exactly opposite statement that's not possible because it's convergent. So that means not satisfied. which contradicts the uniform convexity condition. The uniform convexity condition. And that ends the proof, and that ends this segment of the lecture. Thank you.